In this section, we're going to talk about logarithms. Now, where's this idea of logarithms come from? Well, we've already talked about exponential functions. Now, an exponential function, now remember a function is a process, right? And you'll remember that the process, all right, for an exponential function was, if I take f of x, and I get a fixed number a, for example, and I raise it to a variable x. Okay, this was the process. Now remember that came out to be a one-to-one function. And we'll look at the graph of that shortly. All right, but it's a process, and since it's a one-to-one function, then we can have what's called a reverse process. All right, and you remember that the reverse process had to do with interchanging x and y. Now, when we did that, we had no way of undoing this one here. So what we've done is we've created a function or a reverse process, which we're going to call the logarithm. So it says that for all real numbers y and all positive numbers a, which of course a is the base, right, and x is the variable. And in this case, a can't be equal to 1, okay? And a is in fact positive. 1 would be very boring, all right, because 1 to any power is 1, okay. We're going to say that the logarithm, all right, to obtain y, we take what's called the logarithm in base a, notice there's the base, right, of this variable x, if and only if x is equal to a to the y. So what this is saying is that these are the inverse processes. In other words, a logarithm is the exponent, all right? All right, it's the exponent part, okay? In other words, the expression of log in base a of x represents the exponent to which the base a must be raised in order to get x. Now, a very interesting thing happens here. So if these are the reverse process, let's suppose that I have y equals log in base a of x. And then, of course, if I take the log in base a of x, and let's suppose I make x equals to what we got up here, a to the y, then this becomes, put it here, equal to log in base a of a to the y. Now notice that the logarithm, log undoes the exponent. And notice that we end up here with y, which is exactly what this is. Alternatively, if I look over here, if I look at x is equal to a to the y, and I know that y is equal to log in base a of x, notice that this exponent undoes the log. All right, and I end up with x. So, of course, I get x equals x here. All right, so in other words, these two are inverse processes, and they will become inverse functions. And so in this particular case here, logarithmic form says that we have the exponent y is equal to the log in base a of this variable x. The exponential form, these two are equivalent things. The exponential form of the same thing says that the base a to the exponent y is equal to x. So notice that these are just exactly the same thing, except that they are written either in logarithmic form or exponential form. Right, so let's have a look at some examples, all right, of actually determining that relationship between, all right, the two. All right, so let's roll this up. All right, let me put that there. All right, so let's look at an example of swapping between, all right, these two kinds of forms. So let's suppose I look at a logarithmic form and I look at a exponential form. All right, so let's suppose I have, for example, in logarithmic form I have the log, or no, let's do exponential form. Let's suppose I have 3 to the power of 4 equals 81. Right, so what we have is this form here. So what does that mean? Well, let's identify some things here, right? So this is the base. Okay, this is the exponent. Right, and this is our number. Right, so given that's the case, if I now want to go to logarithmic form, okay, then what I have is that I want to take the log in base 3, so that's our base, of this number, which is 81, is actually equal to the exponent. All right, so notice that that's the exponent. So here's the number, and here's the exponent, which of course is 4. So there's our equivalent logarithmic form. All right, let's go back the other way. Let's suppose I have log, but the base is a half now, right, of 8 is equal to -3. Well, what does that mean in exponential form? Well, again, here's our base. All right, this is our number. All right, and this is going to be, of course, our exponent. Right, so in exponential form, of course, it's going to be the base is a half. The exponent is -3. And this is equal to 8. And of course you can see that that's certainly true because that's 2 to the 1, -1. And of course, let's just do that. We're going to have this as 2 to the -1. The -3 is actually equal to 2 to the 3 by exponent laws, which is 8. So it is certainly true. Okay. All right, let's try another one. Let's suppose I look at exponential form of 10 cubed, we know of course is 1,000. What does that mean in logarithmic form? Well, again, here's our base, here's our exponent, and here's our number. All right, so this is going to be, we're going to look at the base, so it's the log in base 10 of the number, which is 1,000, is equal to 3. Now, the reason for that, of course, is from the relationship we saw that this is 10 to the 3, of course, and the log in base 10 undoes the exponent of base 10, so it's 3. Okay? All right, so next. All right, let's look at another one. Let's suppose that I have log in base 5, all right, of 1 on 125. Is equal to -3. What does this mean? Well, of course, here's our base. This is our number. And this is our exponent. So putting it over here, what are we going to have? Then we're going to have 5 to the -3 is equal to our number, which is 1 over 125. Okay, so we have that. All right, let's suppose I have 12 to the 1, okay, is equal to 12. Well, we certainly know that. 12 to the power of 1 is 12. All right, well, this is the base now. Okay, this is the exponent, and this is the number. All right, so what do we have over here? So this is going to be log in base 12. Right, of the number 12 is equal to 1. Okay. All right, so notice that this would be a power of 1 here, of course, so the log in base 12 undoes the exponent of base 12, leaving us the exponent. Right, let's also look at, let's suppose I have log in base 6 of 1 is equal to 0. What does that mean? Well, of course, here's our base. Okay, here is our number. And here is the exponent. So what this is saying is that 6 to the 0 is equal to 1, which of course we know is in fact true. All right, so that leads us then to looking at solving logarithmic equations. So let's look at that. Okay, so solving logarithmic equations. All right, now to solve a logarithmic equation, all right, basically what we have here is this. If I have two logs of the base, so let's look at a rule here. It's very similar to the rule for exponents. If I have log in base a psi of x1 is equal to log in base a of x2, this will imply that x1 equals x2. So if we can get things in the same base, all right, then we can just equate the argument, what we call the thing we're trying to take the log of. Okay. All right, so let's do an example of this. All right, we're going to solve, okay, in this case here, let's do part A. So let's have a look at log in base A of 16 on 9. Okay, so there's a couple of things we can do here. So that's rule 1, okay, if we can get two logs the same. All right, and we have this is equal to -2. Now, if we can't do that, then what we do is rule 2, change to exponential form. So these are the two rules that we're going to look at. Because remember that if I have a to the x1 equals a to the x2, then certainly a1 equals x2 again. So notice that these are really very much the same rule, just written in log or exponential form. So in this case here, let's change this to exponential form. So notice that this is the base, this is the number, and this is the exponent. Okay, so what do we have then? So this is going to be saying x to the -2 is equal to 16 over 9. Okay, all right, so that's what we have to start with. So what does this really mean? Well, this implies, of course, using our exponent rule says that this is x to the 2 would be this thing upside down. So we'd flip it, okay? So this, therefore, we would say that, of course, x would be equal to, right, the square root of 9 on 16, not the negative of it, because remember the base must be positive, okay? So this will be 3 over 4. So my solution set is going to be the set 3 on 4. Okay? All right, let's do part B. All right, part B, let's suppose we want to solve the log in base 16 of x is equal to 3/4. All right, so again, I don't have a log here on this side, so what we're going to do is, of course, rule 2 again. And so in this case here we have the base. This time this is the number. And therefore this one here is going to be the exponent. So this is going to imply then that in fact 16 to the 3/4 is going to be equal to x. Alright, so this of course means that implies then that 16 to the 1/4 cubed is equal to x. Okay. Now, what is 16 to the 1/4? We're looking for a number when multiplied by itself 4 times gives us 16. Well, we know that 2 by 2 by 2 by 2 gives us 16. So this means that x is going to be equal to 2 cubed, which is 8. Okay. Right, so that's how we do that particular type. All right, let's try one more. All right, part C. Okay, let's suppose then we are looking to solve log in base 36 of root 6 is equal to x. All right, so now we have this is the base, this is the number, and this is the exponent. So this implies then that 36 to the x is going to be equal to square root of x, square root of 6, which of course we know the square root of 6 is equal to 6 to the half. All right, so what I can do here, of course, I know that 36 is actually equal to 6 squared, so this implies then that I have 6 squared to the x is equal to 6 to the half. So I'm looking to use rule 2 again. Notice using the exponent rules I have 6 to the 2x is equal to 6 to the half, which implies that 2x equals a half, which implies x is equal to a quarter. So our solution set here is a quarter. Okay. All right, and so that's how we do those kinds of exponential equations, and later on we'll show you how to do the rule 2. Okay, so next one we want to talk about is functions. Remember that taking the logarithm is a process, and so therefore it's a function. All right, and of course it's the reverse process to exponent, taking the exponent. All right, so we define it formally like this: a logarithmic function. If I have a, of course, here is positive. Okay, it's not equal to 1 though. Okay, and we have x is also a positive number. Then f of x, all right, is equal to the log in base a of x defines what's called the logarithmic function with base a. Okay. All right, now why are these two the inverse of each other? Well, let's go back and look at the graphs of these. So I'm going to look, I've got a free online graph here. You might want to take note of this. All right, it's at www.meta-calculator.com/online/online. All right, so what I'm going to do here is I'm going to look at graphing this, all right? And so, in actual fact, if you go back one here it is here, right there. All right, and so we click on Graphing Calculator, and here's our first equation. So let's just take 2 to the x, okay, and let's graph that. You'll notice that here it is here. Notice that that's what we got for our exponential function. Okay. Now let's look at y equals x, because remember that the inverse function will in fact be a reflection in the line y equals x. And so here's our line y equals x. So we want to reflect this red graph here in this blue line. All right. So let's put in then the log. And we're doing it in base 2 of x, okay, and now let's graph it. Notice that these are a beautiful mirror image, all right, of each other. So the purple one here is a mirror image of the red one in that blue line y equals x. And the reason being, of course, is if you remember inverse functions, is that we interchange the x and y values. Now notice that for the exponential function here, it goes through the point 0, 1, and so therefore the inverse function, the log in base 2 of x, goes through the point 1, 0. So you're flipping them around. All right, notice that the exponential function here goes through 1, 2. And so therefore the logarithmic function must go through 2, 1. Okay. All right, now notice also, you remember that the exponential function had a domain of all real numbers. And therefore the inverse function, all right, we'll have a domain of, a range of all real numbers, because the domain of the function is equal to the range of the inverse function. And you can see that it does. It goes up and up here forever. All right, also we look at the range of the exponential function, which is greater than 0. All right, and notice here that the domain, therefore, of the inverse function, the log function, is greater than 0. All right, so there's our graphs and how and why they are in fact inverse functions. Both the log function and the exponential function, of course, must be one-to-one functions. They satisfy the horizontal line test, all right, and so that's why they can have inverse functions. They're the inverse function of each other. Alright, so basically then we're talking about in general, if I look at a inverse function, if I'm looking at just any base, we know that our exponential function is going up like this. So this is y equals a to the x. Okay? Always goes through the point 0, 1. Okay? Now when we do our inverse function, we interchange x and y. So of course it's going through this, and so we're going down here like this. And this is y equals log in base a of x. Okay? So there's a couple of things that we want to talk about here as far as the characterizations. Which means these are the properties that the exponential function have. Right, first of all, the domain, and this is for y equals log in base a of x. All right, the domain here is numbers which are greater than 0, so it's going to be from 0 to infinity. All right, and that of course was because this one's domain, all right, and range, importantly here, the range is 0 to infinity. Right, the range of this one, all right, is it goes down here forever and goes up here forever, so it's going to be negative infinity to infinity. And that's because this one up here had the domain of negative infinity to infinity. All right, now notice that it is always going up, so it's always increasing. Like so. All right, what else do we know? It goes through the point 1, 0. There it is here. Okay. All right, now notice that this one up here also went through 1a. Okay, so it also goes through a1. Okay, so reverse of those. It also goes here, of course. All right, it goes through here negative 1, 1 on a. So therefore it goes through 1 on a, negative 1. Okay, so there's 3 points that it will go through. All right, now notice here that the y-axis here is a vertical asymptote. Right, because the x-axis was a horizontal asymptote, right, for the exponential function. All right, so there we have, in fact, the characterizations here, all right, of or the properties of the exponential function by means of its graph. Okay. All right, now, of course, this was when a was greater than 0, and of course it's not equal to 1. And of course in this case here, it's going up here, this is where a in fact is going to be greater than 1. That's the graph. Okay, all right, because it went up there. Now you'll remember that of course we had graphs, and we should talk about that. Let's look at the graph of that. Oops. All right, so here it is. All right, so let's go to the equations. This time, let's have a look at, let's suppose I put in here 0.5, which is a half. Okay. All right, we got y equals x again, and now this time we want to look at log in base a half. Well, of course we can't draw that one, so let's just clear that one for a second. All right, and let's draw these two. All right, so notice, see what's happening here. Right, it's now coming down like this. See this? Okay. And so consequently, if we are going to look at the inverse of this, notice it goes through 0, 1 again, so it's going to go through here again. All right, and so what we need to look at is what does this look like as a reflection? Okay. Now, to do that, let's have a look at, let's roll this up a little bit, and let's look at what happens when a is going to be, so we're going to look at the function here now, y equals log in base a of x again. But this time we're going to look at a being between 1 and 0. Remember, a is positive, all right, always. So if we draw this, we just saw what happened. Still goes through 0, 1, but now, of course, it's coming down here like so. All right, there it is there. All right, so this one is y equals a to the x when a is less than 1 and greater than 0. All right, so if we put our line through here, all right, of course, we're going to have this coming down through here again, through this point here. And so it's going to come down here like so. Like this. Okay, and notice that this is y equals x, and again it's a reflection in the two lines. Right, so what are the characterizations of this? All right, well, we go through the same thing. What's the domain now? Well, you can see here the domain is still going to be all of the positive numbers, not including 0. We can't find the log of 0. All right, the range, all right, is all real numbers again, so that hasn't changed. Right, again, it goes through the points, all right, 1, 0 again, okay, and of course it goes through the points 1 on a, -1 again, and it goes through the point a1. Okay, it's just in this case, a, of course, remember, is between 0 and 1. So it goes through these points. Notice it's always decreasing now. Always going down to the right. Okay. All right, we still have a vertical asymptote. Of the x-axis, of the y-axis. All right, like so. All right, so the real thing that's changed, of course, is that it's decreasing. Okay, so notice here, all right, this was increasing, this was decreasing. Very much everything else has stayed the same. All right, so that's how we do that, and the characterizations, all right, or characteristics of the logarithmic function are very important, just like they were for the exponential function. So if we were to graph these, so let's look at an example, and I'll just do these roughly. All right, let's suppose I want to graph each function. Right, then let's do part A. Let's suppose I want to do f of x equals log in base 1/3 of x. All right, so what we do here, all right, is create a table. Now with this table, what we want to do is we want to create, all right, a table with x values, but we want to also, all right, look at the exponent form. In this case, the base is a third, and then we're going to look at the logarithmic form. All right, so let's start with some values. We don't want to get too big of values because remember the functions change quite quickly. So let's just look at, say, -2, -1, 0, 1, 3, and 9. All right, I'm using factors of 3 here. Right, so when I do this, for example, I put -2 in here where x is, I'm going to get 9. Okay, because 1/3 to the -2 will be, of course, 3 to the -1 to the -2, which is 3 squared. And this will be 3. All right, this will be 1. Now, this will be a third. This will be 1 on 27. And if you use a calculator on this one, this is going to get really small. This is a 1 on 19,683. Okay. All right, so now what we want to do is look at this. If I'll take the log of -2, I can't do this. It's undefined. Remember, I can't find the log of a negative number because, remember, the domain of the log function is all positive numbers. So this is undefined as well. Okay. I can't find the log of 0. Remember, it's got to be positive numbers, so this is undefined. Okay. Now we can find the log in base 1/3 of 1. That, of course, is 0, because remember, it always goes through the point 1, 0. If I now look at 3, all right, so if I look at, if I come down here and I say, okay, I want log in base 1/3, all right, of 1 on 27, this is equal to the log in base 1/3 of 1/3 cubed. So that, of course, will give me 3, because the log in base 1/3 undoes the exponent in 1/3, base 1/3. And so this one here, all right, if I look at 9, sorry, I did that one wrong. All right, so what I'm looking at here, of course, this would be 3, but what I'm looking for is the log in base 1/3 of 3. So now if you write this in log form, 3, of course, is 1/3 to the power of -1, because that would, of course, cause us to 1/3 to the -1 is 3. So now I've got it in base 1/3, so this is actually -1. So we can put -1 there. And 9, of course, is much the same. We put in log in base 1/3 of 9 is actually equal to the log in base 1/3 of 1/3 to the -2. Okay, which of course is equal to -2. So I end up with -2. All right, so if I now do just a rough sketch of this. All right, here's x, here's y. Okay, we know it goes through the point 1, 0. That's the easy guy. That's that one there. Okay. Now, it can't go through -2, -1, that, because, of course, the y-axis is always an asymptote. So it's coming down here, like so. Now, where else does it go through? Well, it goes through 3. So let's go 1, 2, 3, and it goes through -1. So here's -1, and here's -2. All right, and here's 1, 2, 3. Oh, 9 is way up there, so I'll have to just leave that out. So we'll get that going around like this. And so here's y equals log in base 1/3 of x. Okay. All right, so let's do a second one. Now notice it's important, before I move on, this is important here that you pick good values. Notice I've got powers of 3 here, right, because this is 1/3 as our base. All right, let's do part B. Suppose we want to graph log in base f of x is equal to log in base 5 of x. Okay. All right, so again, we set up our table of values of x. All right, now we're going to have 5 to the x, and we have log in base 5 of x. Okay. All right, so we're going to start with, all right, some good values that are in base 5, so some smaller values. So let's go, say, 1 on 25. Let's go 1 on 5, all right. Let's go 1, and we can't find 0. And we're going to have 5 and 25. Okay. All right, so in this case here, if I look at these, so what do I mean by this? Well, of course, this is 5 to -1. See that? Okay. All right, and this is 5 to the -2. Okay. All right, so, and of course, this is 1 here. So when x is 1, clear to get 5 here. And when it's 5 here, well, that's going to start to get big. So we might just leave this section out because they're going to start to get really big. All right, so let's have a look what happens here. When I put that in 5 to the negative 2 in here, the log undoes the 5, so I end up with negative 2. Here it undoes it, so notice that what we have here, log in base 5 of 5 to the negative 2 is equal to negative 2, because the log in base 5 undoes the exponent in base 5, so this one will be negative 1. Now this one's actually easier to draw, so this one will be, when I do 1 here, of course, log in base 5 of 1, of course, will be 0, because we always know that the log function goes through 1, 0. When it's 5, of course, this is 5 to the 1 is equal to this, so that would be 1. This is 5 squared would be this, so this would be 2. So when I draw my picture, here's my graph, y, x, right, we always know it goes through 1, 0. That's this point right here, okay? Right, now when it goes through, y is going to be negative 2 when we get 1/25th, so that's really small. And that's going to be 1/5 when it's negative 1, that's very small too. All right, when it's 2, it's going to be when x is 5, 1, 2, 3, 4, 5, we know it's going to be 1. Now, of course, 25 is too big, so we'll just leave that one out. So it's coming up here, close, around here, and goes like this, like so. And so this is our y equals log in base 5 of x, okay? Right, now the interesting thing is that we can do all the translations. So let me move up here. Right, we can use all the normal translations, right, to graph logarithmic functions. Now you remember that the translations we had stretching and compressing, right, vertically and horizontally. Right, we had shifting, okay, and reflecting. Shifting up and down horizontally, all right, that was vertically and horizontally. Right, so we can do much the same here, so I'll just do one example of this. Example, let's suppose we want to graph f of x equals log in base 2 of x minus 1. Now notice we're taking the function here of x minus 1, so the x minus 1 is done first because it's in the parentheses there. So in other words, this is a horizontal shift. Right, horizontal shift to the right. Right, so in other words, if I draw this, I know that it goes through here, so I'm going up here, here it goes. This is y equals log in base 2 of x. All right, so this point here is 1, 0. Now we're moving it to the right, all right, 1 unit. So this point comes across here to 1 unit. So this would be 2, 0. So in other words, it's coming up here like so, like that. Okay. All right. So we just shift we just shift everything across 1 unit. So in actual fact, everything should come across 1 unit. All right, like so. All right. All right, so that's that. Let's do one more quick example, perhaps. All right, so let's do an example here. Let's suppose we want to do let's do a double one here. Let's do graph y equals log in base 2 of x minus 3 plus 2. Alright, so in this case here, I'm just going to do this roughly. We know the original function does this. It goes through here, alright, and so forth. So this is y equals log in base 2 of x, our fundamental function. Right, what does the negative 3 do? Well, that, of course, moves it across, and I'll need more space here. So here's 1, 2, 3, 4. So it moves everything across 4 points. So we do something like this. Alright, so this would be y equals log in base 2, going across 3 units here. 3 units to the right. Alright, like so. Right, now what does the plus 2 do? Well, it takes this and it goes up 2. So we're going to shift everything up 2. So everything is up 2 units. Like this, so this is y equals log in base 2 of x minus 3 plus 2. Okay? Alright, so that's how we do our transformations. Right, the next thing we want to talk about are properties of logarithms. Right, now remember we had properties of exponents. Alright, of exponent properties. Alright, so let's do that. Remember that a to the x by a to the y was equal to a to the x plus y. Notice we added the exponents. Alright, a to the x divided by a to the y was equal to a to the x minus y, and so forth. A to the x all to the power of y would came out to be a to the x times y, and so forth. Well, we have the same kind of parallel things here, right, for this, because remember that the logarithm is the exponent. So notice that when I'm doing the product of 2, so let's do, I'm doing the product of, say, 2 numbers x, y. Right, that's really what we're talking about is the product, all right, when we do the product of the exponents here, which means we add the exponents. When we do the product of these two exponentials, we add the exponents, so therefore we would add the logs, because that is the exponent. So that's our first rule. Second one is if I am now dividing, then of course we subtract the exponents, so this will be log of in base a of x minus the log in base a of y. Number 3, right, this is called the power property. If I take the log in base a of x to some power r, right, then this of course knows we do the product here, so this is r by log in base a of x. Okay, so that's it. We know, number 4, that the log in base a of 1 is always 0. And we know that the log in base a of a, which is 2 to the 1, is the exponent, which is 1. Okay, so these are the properties that we're going to now use. All right, so let's do some examples. Right, so example 1, let's rewrite each one of these. Right, so let's rewrite each of the following, and we're going to use our log rules here. Now, assuming here that all variables are positive real numbers, and of course we know that a can't be equal to 1, right, and in this case b can't be equal to 1 if we have a different exponent. Alright, so let's look at part A. Let's suppose I want to do the log in base 7 of 8 times 6. Well, this is log in base 7 of 8 plus the log in base 7 of 6, because that's our rule number 1. Okay. Part B, let's suppose I want to do the log in base 6 of 12 over 5. This would be log in base 6 of 12 minus log in base 6 of 5. Okay. Right, next part C. Let's suppose we want to find log in base 2 of the cube root of 9. Well, the first thing I'm going to do is I'm going to write the cube root of 9 in exponential form, which is 9 to the 1/3. Now I'm going to use the power rule, which says the 1/3 comes in front, log in base 2 of 9. So that's rule 3. And this one was rule 2. Okay. Part D, let's suppose I want to look at the log in base B of RST, let's make it S squared T, over U cubed V to the 5. Right, now, the order of this is fairly important, so I usually do the quotient first. So this would be log in base B of RS squared T minus log of U cubed V to the 5. Right, now we have products here, so this will be log in base B of R plus log in base B of S squared plus log in base B of T minus, I'm going to use parentheses here, all right? This is going to be log in base B of U cubed, and this is a product here, so plus log in base B of V to the 5. So this is going to be log in base B of R. Bring the power rule here into play, so we have log in 2 times log in base B of S plus log in base B of T minus, bring the power rule in, I'm going to distribute now, so it's going to be 3 log in base B of U minus 5 log in base B of B, and there we have. So notice we've taken this complicated product and quotient and turned it into the sum and differences. All right, let's do part E. All right, let's suppose that we want to find the log in base A of the 5th root of R cubed. Right, so I'm going to first of all write that in exponential form. So this is R cubed to the 1/5, which your exponential rule says this would be R to the 3/5. Now I'm going to apply the power rule, and there it is. Okay, and finally, all right, let's do a log in base A of the mth root of R cubed S squared over T to the 4. Okay, first thing, all right, I'm going to write this as log in base A of R cubed S squared on T to the 4 to the 1 on M power. I'm going to apply the power rule first, all right, because it's going to get complicated otherwise, and we end up of R cubed S squared on T to the 4. So this is going to be equal to 1 on M. Now I need to use a parenthesis here. So it's going to be log in base A of R cubed plus log in base A of S squared minus the log in base A of T to the 4. Okay, so this is going to be now 1 on M by 3 log in base A of R plus 2 log in base A of S minus 4 log in base A of T. Okay, right, now if you want to write this out without the parentheses, you get 3 on M log in base A of R plus 2 on M log in base a of s minus 4 on m log in base a of t. And that would be my result. Right, now we can go back the other way. And let's look at going back the other way to make a large sum and difference into one logarithm. So again, we're going to write each of these as a single logarithm. Right, part A. Let's suppose I have log in base 4 of x minus log in base 4 of y plus log in base 4 of z. Okay, so this of course is equal to the log in base 4 of x divided by y plus log in base 4 of z. That's using the quotient rule in reverse, so this is going to be log in base 4, now it's the product, so it's xz on y, and that would be my single logarithm. Right, part B. Right, let's suppose I have 4 log in base b of r minus 5 log in base b of s. Alright, so this is going to be log in base b of r to the 4 minus log in base b of s to the 5, which of course it's the difference now. This is going to be log in base b of r to the 4 over s to the 5. And that would be my single logarithm. Right, finally, let's do one a little bit more complicated. Let's suppose I want to look at 1/3 log in base a of x plus 2/3 log in base a of y minus log in base a of xy. Okay? Right, so the first thing I'm going to do here is I'm going to take out 1/3 out of these two here. And of course, that'll be y squared if I use that there, minus log of x, y. Right, so this is now going to be 1/3 log of x, y squared, all right, minus the log of x, y. This is in base a. So this is going to be the log in base x, y squared to the 3rd power, all right, divided by x, y. Okay. All right, so I think the best way to write this, then this would be the log in base, and these are all in base a. Right, base a of the cube root of x, y squared over x, y would be my result. All right, now what about numerical values? All right. Well, we're going to look at numerical values of log functions. So let me do an example here. All right, and let's suppose we're given, all right, that the log of 10 of 7 is equal to 0.8451. All right, then let's find, so let's suppose if that, which it is, right, then find part A. Let's suppose we want to find log in base 10 of 49. Well, if we can write 49 in terms of 7, which we can of course, which is 7 squared, then this of course is equal to 2 log in base 10 of 7 using our log rules. So this will be twice 0.8451, which you can use your calculator on that. It comes out to be 1.6902. Right, part B. Let's suppose I want to find the log in base 10 of 70. Well, of course, log in base 10 of 70 would be the same as 7 times 10, which of course would be the log in base 10 of 7 plus the log in base 10 of 10. Now we know that the log in base 10 of 7, we'll find that in a minute, plus, but the log in base 10 of 10, of course, is 1, because that's a power of 1, undoes it and gives you exponent. So this is going to be 0.8451 plus 1, which is 1.8451. So we can find numerical values here. So the important thing to remember here is that we have used quite often, all right, this particular thing, that a to the log in base a of some value x is equal to x. Now remember, x has always got to be positive if that's the case, all right, because we can't find the log of a negative number. And the other one, which just remind you that we talked about, was if I take the log in base a of exponent of base a, then it undoes it and I end up with x. And so these are two very important, all right, relationships. And notice that we did use it right here. Okay. All right, so that's the end of section 4.3.